What's going on, everybody? This is Mr. Diamond picking up where we left off. Now, you might notice things are going to be a little bit different here. First of all, in the bottom right-hand corner, we do not have my face, and that is because I'm recording this at home due to some technical difficulties I was having getting this to be able to work on my board at school. So we're going to pick off where we left off talking about carbon and talking about hybridization specifically. Now, you don't know what that term means. I don't feel bad because that you aren't supposed to yet. But the question I left you off was, let's think about carbon, specifically methane. Experiments and data have shown that all bond lengths on a molecule of methane are the same, and the angle is identical, and that each bond is covalent, I didn't catch that last time. I think I was pretty sleepy that last video, as I'm sure some of you noticed. Notice carbon will form 4 bonds. Taking into account what we know about carbon, why might that be weird? Now, this was a very complex question, so I don't blame you if you don't actually know or couldn't figure out what the answer was. So we're going to switch over to the hand cam, which is why we are on I don't have my face and why I'm doing this at home. So we're going to switch over to here. And let's think about, let's see, I think I've got a better pen over here. So we're going to think about methane. Methane, make sure that we've got this so we can see it good. So methane will look something a little bit like this. Each of these dots are a hydrogen, and then that middle point right there is a carbon. We did that in our skeletal structures. I hope my camera is going to stay in focus for this. And we also know the distance between each of these bonds. And you may have to go back and actually look that up from chemistry if you don't remember. We can actually pull it back up on, make sure I get the right one. There we go. We can actually back up just to make sure we're on the same page. So tetrahedral right here. Tetrahedral has 4 pieces. They're all attached. This would be our carbon. These would be our hydrogens. So 109 degrees is what we're going to go with. So we're going to switch on back. So 109 degrees. And the question was, why might that be weird? So what do we know about carbon? Well, carbon has, looking at the periodic table, it has 6 protons. That seems like it might be important. Average atomic mass of 12. So usually has a mass of about 12. Technically, it's 12.011. So we'll put a little question mark on there, though. So what is there that could be weird? And this is something that you shouldn't feel bad about, that you've probably never actually thought about, never actually worried about. But the fact that it makes 4 bonds like this is weird. And to explain that, we're going to draw our electron configuration, but we're going to do it in a slightly different way. So one way that you can draw electron configurations is by putting a line here. We're going to make this energy. And then as you increase up there, we're going to have higher energy. So the first electrons are always placed on 1s. Then we're going to move slightly over. We'll have 2s. And then a little bit higher than that, we're going to have 1, 2, 3, 2p. So carbon has 6 protons. That also means that usually in its normal state has 6 electrons. So 1, 2, 3, 4, 5, 6. Okay, that makes sense. This is exactly as we would have done. That is the electron configuration. I'm going to pause the video really quick just to try to make the camera a little bit more cooperative really quick. All right, I am back. Hopefully that should not do any weird autofocus stuff anymore. Okay, cool. Now the reason this is weird, and I'm going to get a different color, so you may want to get a different color for this as well. Unfortunately, I don't have a ton of different colors at home, so it looks like we're going to be stuck with purple. Let me dig through my backpack real quick. And try not to sneeze in the microphone. Yep, looks like all I got is purple. Excuse me. Okay, So the 4 electrons that it needs are here, 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 and here. And so in this case, purple represents needed. And so you might be going, well, this still doesn't seem very relevant. I'm still kind of confused as to what the weird part of this is. What shape do p orbitals have? Well, p orbitals have a shape where they kind of come up in this dumbbell. And we have one going side to side. We have, or up and down, one going side to side. And then we have one that kind of goes in and out. So you could think of this as our y, this is our x, and this is our z. If these are where the electrons are planning on being bonded, shouldn't there be bonds on these 3 axes? Shouldn't the one bond go vertical to correspond with the y, one bond go horizontal to correspond with the x, and then the last 2 electrons go in and out for the z? Why would this be the position? Why would it make 4 bonds to 4 distinct things when 2 of the electrons are supposed to go to the same place? That doesn't make sense. And the reason for that is because things get a little bit more complicated than that. In the S, there's just a straight line. There's no connections. In P, everything would be 90 degrees apart from one of the other ones. But in this case, they're all 109 degrees apart. So what we're actually going to do is this empty spot. And so I'm gonna scoot this over a little bit. So we're gonna continue its being about energy. Our 1s is gonna stay the same. It's going to be an up arrow, and it's going to be a down arrow. Our 2s is going to be right here, and then our 2p right above it. This first electron is going to stay there, and then these electrons are going to stay there. But I'm going to switch to a pencil. This, I wish I had a better color, but, you know, I'm a hack and a fraud. So this gray down arrow electron that looks pretty similar to the other ones, unfortunately, this electron is actually going to get stolen, and it's going to jump up here to this spot, and it's going to move there. Now, in doing that, first of all, that breaks rules that you guys have learned. But as you've probably realized, some of the rules that you learn are just kind of common rules. They don't actually exist and work that way all the time. So now we've got our 1s. We've got our 2s that has 1, and then our 2p that has the 2 ones it was going to normally have, and it has this last electron. And that's weird. Our rules told us that we needed to fill electrons low energy to high, and this was going upwards in energy. So this one should have been full before this one. But by losing that electron, it's actually giving up a little bit of energy to the p. It's making it more stable, and so it's actually going to cause this p orbital, because it's more stable, to scoot down a little bit, and it's going to cause this s orbital to scoot up just a little bit, and that will actually get them to be on the same level. And so you'll end up with what was originally an s, a p, and a p. And it'll be 4 lines in a row instead of 3 lines in 1 line separated into 2 different parts. Now, we can't actually keep this S distinct anymore because they're all on the same energy level. So what's actually going to happen is these guys are going to go through a process called hybridization. And you may have heard of hybrids, things like zorses, zebras and horses, ligers, lions and tigers breeding together. In this case, this is going to be a combination of S and P. So we're going to group all of this together, and basically all of these electrons are going to say, look, we're no longer in the P section, we're no longer in the S section, we're going to be a new thing entirely. So our hybridization is going to result in 1, 2, 3, 4 sp3. So this would be technically on energy level 2, but usually you won't have to care about that. But this is going to be an sp3 hybrid orbital. And what that means is it's mostly like a p orbital. It's 3 parts p orbital to 1 part s orbital. So it's 75% of a p orbital. But because it has that little bit of s, it's going to twist and bend the shapes that it would have normally been in. It's no longer going to be the up and down, left and right, in and out. It's now going to have 4 points that are spreading apart, 4 different locations that it needs to have space for. And the way that it can have 4 of those locations, just like we talked about when we originally learned about this in chemistry, is that they have to get as far apart as possible, and the way to do that is to form a tetrahedral geometry. So to recap and go through this step by step again, and explain this whole picture again, because you are going to have to explain the process of hybridization. That is one of the things that I will require you to do on the test. Carbon has 6 protons, therefore usually has 6 electrons. During electron configurations, we move from low energy to high energy, and you would result in something that had 1s2, 2s2, 2p2. And that would leave only 3 of the lines that actually need anything. That goes against what we know about it being a tetrahedral geometry, about it having 4 bonds instead of just, put my hand in there, 4 bonds instead of just 3. And the reason for that is because to help stabilize this, that 2p is kind of like, if I would just had 1 more electron, I would be at this more stable energy point. I would be half full of electrons. And so this 2s electron will actually pop up into the 2p. Doing so is going to lower the energy level because it's going to make this more stable, but it's also going to raise the energy level of the 2s because now it's less stable. And that's going to actually cause them to meet in the middle and result in 4 orbitals that all are occupying the same energy level that are 1 part s, 3 parts p. And we call that process hybridization, and we would therefore have an sp3 hybridized orbital that would have 4 up arrows and could then make 1, 2, 3, 4 bonds connecting it to it. Okay. That is a very weird concept, so don't freak out if you're like, this doesn't make a whole lot of sense to me. That's a pretty common response to this. It's a very advanced topic. It's part of the reason this chapter is so brutal. I would recommend watching this video a couple of times if you get stuck on this idea. On the question, you will be allowed to draw pictures and to help explain it. Just simply redrawing this would not get you the full points. So don't think you can just memorize this picture. You have to be able to actually explain things along the way. You would need to add little notes and add little things along here that I'm not going to add because I don't want you to just be able to memorize this picture. So we're going to hop back into the notes again. And we're going to go back and look at how we can use this hybridization. So pulling this back up, the simplest way to determine the hybridization of an atom is actually just to use steric numbers. And if you know the steric number, you can figure out the orbitals that have been hybridized. So in CH4, carbon is attached to 4 substances, so it is a sp3 hybridized orbital. I'm going to post another video working on an example of this, but if I go to my next slide here, we've got a question of determining the hybridization of the following atoms. And I will work out this example on another video, and I'll talk a little bit about the last couple slides here, which is an exception to the rule. I think this is enough for one video, and I want to make sure that you're able to kind of watch this in one go and be able to come back to it and know that you're getting all of the stuff related to hybridization. So I hope that makes sense. I hope you have a good rest of your day, and I hope to see or hear from you soon.